And then 14.7 is going to be on finding maximum and minimum values of a function. And so we get some definitions here for local max and local min, absolute max, absolute min, and they're very similar to the ones you had in Calc 1. So it says a function of two variables has a local maximum at the point AB if the function values at points close to AB are less than or equal to the function value at AB. And remember, the function values give the z coordinate. So f of AB would be here, and then all of the other z values would have to be lower than that. So it's going to look like the top of a hill. So that would be a local max. And then local min, it would just have to be, so there's f of AB, and then all of the other z values around it are bigger. So it would be at the bottom of a hill or valley, whatever you want to say. That's local max. Absolute max is if it's the biggest one on the highest z value on the entire graph. Like we saw, like when we had those sine of x plus y, where it almost looked like those foam cushions where it just had little bumps all over the place. That had lots and lots of local maximum. If they got like bigger or smaller the farther you went out, then each of these little peaks would be a local max, but if the graph then did this, then we would only have one absolute max. The absolute max is just the highest point. Now, in the case of the one we had, like in lecture notes and on the project, where they were the same height every time, every single one of them is an absolute max because they're all the greatest z value for the function. And then that very smallest z value is the absolute min. Okay, the theorem we have says if f has a local max or a local min at a point AB, and the first order partial derivatives of f exist there, then both of the first partials have to equal 0. Okay, so this says if they exist, they're 0. What's kind of implied here, and it's very subtle, is that, and this was just like what happened in Calc 1, you can have a local max where the derivative doesn't exist. Like I could draw a picture like that, right? There's a local max here, the derivative is 0, but there's also a local max here, and the derivative doesn't exist. So when we look for local max or local min values, we're going to look for critical points, which is where both of the first partials are 0 or one of those doesn't exist. So, and those points will be candidates for local max or min. Just because those things happen doesn't mean it's a max or a min. And an example from Calc 1 is if we had a graph like that, where it flattens out, the derivative is 0, but that's not a max or a min, right? You don't, this is not the top of a hill because you clear it and you go uphill again. So just because the partials are 0 doesn't mean there has to be a max or min there. It's just those are the candidates for where a max or min could occur. Okay, and then in Calc 1 we had a second derivative test to tell whether something was a local max or a local min if the first derivative was 0 there. Now, when we have a function of two variables, there are 3 different second derivatives. There's the partial with respect to x twice, the partial with respect to y twice, and then the partial with respect to x then y. So we have 3 second derivatives. And the second derivative test for Calc 2 involves all 3 of them. So it says, suppose the second partial derivatives are continuous on an area centered at the point where we think there might be a local max or min. The first partial derivatives are 0. Then they define this capital D to be the product of the second partial with respect to x times the second partial with respect to y minus the mixed partial squared. And then we have these three different conditions. So it says if d is positive and the second partial with respect to x is positive, well, let's think about this expression. So we have f sub xx, f sub yy minus f sub xy squared. And they're telling us this entire expression is positive. And we also know that this is positive. What does that imply about f sub yy? It has to be positive. Because if f sub yy were negative, then we'd have positive times negative, which would be negative, and then minus a positive number. So that entire expression would be negative. So f sub yy has to be positive. And remember from Calc 1, what the second derivative tells us about is concavity. And if the second derivative is positive, the graph is concave up, right? So this means concave up parallel to the x, and this means concave up parallel to the y. So think here's concave up parallel to the x, and then here's concave up parallel to the y. It doesn't look so good there, but here concave up parallel to the x, concave up parallel to the y. So what must happen at that point? It must be a local min, because it's at I'm creating like this bowl shape, and it would be at the bottom of the bowl. So so if these things happen, then there's a local min at AB. Yep. Mm-hmm. Okay, and now let's look at this. So I'm still thinking about f sub xx, f sub yy minus f sub xy squared. Again, they tell us it's positive, but this time they tell us that f sub xx is negative. So what must be true about f sub yy? It has to be negative, right? Because two negatives will make a positive. If this was positive, then we'd have negative times positive, which would be negative, and then subtracting a positive. So if the entire expression is positive and f sub xx is negative, then f sub yy has to be negative in order to make this term positive. So now second derivative negative means concave down. So parallel to the x, it's concave down. And now parallel to the y, it's concave down. So down and then down. So what must happen at that point? There's a local max. C says if the D is negative, then f sub AB is not a local max or a local min and is called a saddle point. Now, just knowing that this whole expression is negative doesn't really tell us anything about any of the signs of those three derivatives. I mean, I know the squared part has to be positive, but I could still have these multiplied together be positive, subtract a number, and get a negative answer, right? 4 minus 7, they're both positive, but my answer is negative. So we're not going to prove anything about signs here, but we'll just think that pretty much always when this happens, that means one of them is positive and one of them is negative. That doesn't follow straight from just algebra, but it takes a little more than that, but we're not going to go that deeply into it. So if one is positive and one is negative, so think in the x direction, it's concave up, or I guess that would be in the y, parallel to the y. And then in the other direction, it's concave down. So, and the reason they call it a saddle point is, say we, I'm going to extend this one down a little bit more. So what the shape looks like, so I'm just kind of drawing another parabola at either end of the downward facing parabola. Just have that come up a little more. So the reason they call it a saddle point is this is sort of shaped like a saddle. If you go parallel to the x-axis, that point looks like a maximum. If you go parallel to the y-axis, that point looks like a minimum. So depending on which way you're looking at it, it could be either or. But it's not classified as a max or a min. That they call this point a saddle point. Maybe the easiest, if you want to draw it, probably the easiest way to draw it is to do kind of 3 parabolas. So do like one in the back, one a little bit lower in the middle, and then one at the front that's about the same height as the first one. And then connect the vertices, connect the front edges, and then connect the back edges. It's hard to get used to drawing 3-dimensional stuff, I know. Okay, so let's look at some examples. And here I've given us graphs from Maple so that when we're done we can just verify what we find with what we see in the graph. So part A says find the local extreme values and saddle points of the function if there are any. So the first thing we need to do is find f sub x and f sub y. So f sub x. Anytime we start with an exponential, we automatically get the exponential back. E to the 4y minus x squared minus y squared. And then that would be times what? Negative 2x. And then f sub y. So again, we automatically start with the exponential function. And then times what? Negative 2y, right, plus 4. We'll have that 4 from the first term. So we need both of them to equal 0, or find where they're undefined. But negative 2x, 4 minus 2y, those are polynomials, continuous everywhere. The exponential function is continuous everywhere. So we need to find where both are 0. And I'm going to write this, I just talked about it, but I want to stress it. Or where either is undefined, but we just mentioned these partials are never undefined. But that might not happen in future problems. Okay, so I'm going to set each of these equal to 0. So I get negative 2x e to the 4y minus x squared minus y squared equals 0, or 4 minus 2y times e to the 4y minus x squared minus y squared equals 0. So if we have two things multiplied together equals 0, we just set each of the two expressions equal to 0. So we get negative 2x equals 0, or e to the 4y minus x squared minus y squared equals 0. What about that second equation? It's what? What about this equation? Is e to the 1 equal to 0? Right. E to any power is always positive, right? The graph of e to the x looks like this. It never is equal to 0 or a negative number. So this one has no solution. The first one, we would just get x equals what? 0. So the second one, obviously we know, for the same reason, the second factor is not 0, so it must be the first factor. 4 minus 2y has to equal 0. So 4 has to equal 2y, which means y has to equal 2. So, and then, now this one we only had one x value and one y value. If we had gotten more solutions in this one, we'd have to come up with all possible pairs. So we'd have to use all the x's from this one and all the y's from that one, and vice versa. The y's from this one, the x's from that one. Now we just got one of each. So the only point, the only critical point for this function is 0, 2. Now we still have to see, though, if we want to see if that's a max or min. Now we can tell from the graph, but in general, you're not always going to be given the graph. So that's where we try to find that capital D. So now we have to find all of the second partials. So we need f sub x, f sub y, and f sub xy. Okay, so f sub x. So here's f sub x. Do we need to use the product rule? Yes, there are two functions of x. So it's the first times the derivative of the second. Oops. And the derivative of the second is just negative 2 plus the second times the derivative of the first. Well, actually, f sub x is the derivative of the first, right? Just to make it easier to evaluate later, and also we're going to have to find f sub xy, we're going to have to take the derivative of this expression with respect to y. So I want to make it look as simple as possible. So I'm going to factor out a negative 2 and the exponential. So negative 2 e to the 4y minus x squared minus y squared times. So if I factor that out, we only have 1 left in the first term. And then I factored out the negative 2 and the exponential, so I have negative 2x squared left. So that's f sub xx. Let's go ahead now. Let's just go straight to f sub xy, and then we'll do f sub xy. Oh, never mind. It doesn't matter. But since we were just dealing with f sub x, let's take the derivative of this expression with respect to y. So do we have to use the product rule here? No, because negative 2x is a constant if we're taking the derivative with respect to y. So negative 2x is a constant that can stay out in front. And then we get the exponential part. And then the derivative of the exponent with respect to y is that 4 minus 2y. I think the only thing I'll do is just distribute the negative 2x in through the parentheses. So I'd have negative 8x plus 4xy. Okay, and then f sub y. So we go to f sub y and take its derivative. So do we need to use the product rule? Yep. So first, times the derivative of the second, which will be negative 2, plus the second times the derivative of the first, and then we have to use the chain rule to take the derivative of that, so that now times the derivative of what's inside. I think for now I'm just going to factor out the exponential part. We could factor out a 2 or a negative 2 as well, but I think I'm just going to only factor out the exponential. So then I would have negative 2 plus, and then 4 minus 2y quantity squared. Okay, so now we've found all of the second partial derivatives. So now we want to find that d, which is f sub x, f sub y minus f sub xy squared. And we just find it at the point 0, 2. So f sub xx at 0, 2. Okay, so I'm going to go look at, here's our f sub xx. So we have negative 2 e to the, okay, so 4y will be 8 minus 0 minus 4 times 1 minus 0. So we have negative 2e to the 4th. And is that positive or negative? Negative. E to the 4th is positive times negative 2. So what this means is it's concave down in the x direction. So it's either going to be a local max or a saddle point. And now let's find f sub y. 0, 2. Okay, so I know the e part is going to be e to the 4th times negative 2 plus 4 minus 2y. Well, that's 4 minus 4, so that's just 0. So we have negative 2e to the 4th again. So as long as the whole expression d is positive, then it will be a local max. Okay. So, but we should find f sub xy still. So 8x, so that's 0 plus 0. So that's just 0. So d is equal to negative 2e to the 4th times negative 2e to the 4th minus 0 squared, which is 4e to the 8th, which is positive. So that, along with the fact that both of the f sub xx and f sub yy were negative, means that we have a local max. Now when they say find the local extreme values, when they say values, that means the z coordinate. All I did was say where it happened. I didn't say what the maximum value was. So all we have to do is just plug 0, 2 into this function. So we'd have f of 0, 2, which is e to the 4th. And now let's look and make sure that everything seems to match with our graph. First of all, does it look like the maximum occurs at the point 0, 2? Yeah, the x would be 0, so that means not towards us or back. And the y is 2. And I tried to make it transparent. You can sort of see the 2's right here. So yeah, it looks like it's happening right above that point. And e to the 4th is about 55. And yeah, that looks about right. So this one didn't have any saddle points. It only had the local maximum value, which also happens to be an absolute max in this problem, and where it occurred. Okay, let me see what the group work is. Okay, I'm going to stop there, and I'm going to have you do numbers 1 through 3.